Hi everyone. Today I'll be talking about my research project titled The Optimal Number of People for Indoor and Outdoor Physical Distancing Using the Pigeonhole Principle. Physical distancing became especially important during the COVID-19 pandemic, but it matters beyond disease prevention, whether in concerts, evacuation planning, or wildlife conservation. My goal was to answer a key question: what is the maximum number of people or objects that can safely fit into space while maintaining a minimum distance? To explore this, I used both theoretical mathematics and computer simulations guided by the Pigeonhole Principle. The Pigeonhole Principle is simple. If you place more objects into fewer containers, at least one container must hold one object. For example, if you randomly pull five socks from a drawer with four colors, you're guaranteed at least one matching pair. This principle also appears in number theory problems such as choosing subsets where no two numbers sum to a multiple of 7. In my research, instead of socks or numbers, the pigeons were points placed inside a geometric space, and the pigeonholes were regions of that space. So, uh, Basically, I created simulations in Java where the mathematical proofs set upper limits, but what happens in real life when people or objects are moved randomly? To explore this, I built simulations in processing Java. The program repeatedly places points in triangles and measures the smallest distance. Running these simulations thousands of times gave me average distance and standard deviations showing how real-world randomness compares to theory. So to apply these simulations, I applied this framework to three real-world contexts. The first one being the concert audience distancing, where I simulated 100 audience members moving slightly in a concert venue. If the minimum spacing is set to 1 foot, safe configurations drop rapidly as density increases. Interestingly, I also calculated potential ticket revenue, about $50 per person, to show the trade-off between safety and profit. This highlights how planners must balance health and economics in multiple aspects. Next, I modeled 10 gorillas roaming in a 3,000 feet squared habitat, each requiring a 100-foot territory. Despite a large space, overlaps occurred frequently because beyond a certain density, territories can't remain exclusive. This has implications for conservation planning, showing how many animals can actually coexist in a reserve without conflict. Finally, I also simulated cars moving through one lane, a 2,500-foot tunnel at speeds between 40 to 60 miles per hour. Even with a modest traffic, faster cars catch up to slower ones, often violating a 50-foot safe following distance. This reflects the Pigeonhole principle. Once too many cars are in a tunnel, safe spacing becomes impossible. These insights could help in designing roads, tunnels, or even algorithms for autonomous vehicles. So, across all scenarios, one lesson stands out. The Pigeonhole principle sets a hard theoretical limit on how many entities can coexist in a given space without overlap. But simulations show that real-world conditions usually perform worse than its maximum. This means while the Pigeonhole principle is a useful mathematical safeguard, in practice, planners often need to be even more conservative. For example, wildlife conservation may require strict spacing, while concerts might be compromised slightly for financial viability. So, extending from this, the future directions that I could possibly include are testing irregular room shapes and natural landscapes, which are kind of irregular factors that we don't consider in our daily life, and also adding agent-based behaviors. For example, how crowds naturally cluster near stages or exits instead of a random generation of movements. And finally, also creating software tools for venue planners, conservation analysts, or engineers to simulate layouts before making decisions. So the ultimate goal is to move from abstract math to practice tools that balance safety, efficiency, and real-world constraints. In conclusion, the Pigeonhole principle provides a powerful way to model physical distancing, whether for human gatherings, animal habits, or traffic systems. It helps us to understand the limits of safe spacing. By combining proofs with simulations, we can apply the ancient principle to modern challenges, ensuring not only safer environments but also smarter designs. Thank you for listening.